Hello and welcome back to Crystallography for everyone. In this video, we are going to go over the concept of a lattice. I believe this is one of the most important topics in crystallography. This definition is likely to come up in almost every video in this series, and for that reason, it is very important that we really get a solid understanding of it before we move forward. I've already written out the definition here. That is, a lattice is a periodic array of points where each point is indistinguishable from any other point and has identical surroundings. I think that the easiest way to begin to understand this definition is to work from one dimension up to 3 dimensions. In one dimension, we are just looking at a line. I'll define this line as extending in the minus x direction and in the plus x direction. And on this line, I can draw points. These are the lattice points. These points are each spaced a distance a, and I can define a vector between 2 nearest neighbor points. We'll also call that the vector A, where the vector A equals the magnitude A times x hat, or a unit vector in the x direction. I think it's very important to be thorough with these definitions. It will save a lot of confusion later on. This is a periodic array of points. Each point is spaced a away from one another. If you're moving along this line, you can expect to see another point every time you move a distance a. The points are indistinguishable from one another and have identical surroundings. I think that these are somewhat coupled definitions. I like to imagine this as if we were standing on a particular point. If we were standing on this point here, we'll call it point 1, and we looked to the right, we would see another point a away, and if we were to look to the left, we would see another point a away. Each point looks the same. In fact, they also look the same as the point that we are currently standing on, and they look the same as the point that is 2a away on each side. Going a step further, it's actually impossible to tell if we are looking to the right or to the left. In each case, we see points, each spaced a away, going off to infinity. It is possible, however, to define somewhat of a roadmap to get around this lattice, and that would be known as a position vector. I can define a position vector r. I'm going to define it in terms of a, the lattice translation vector, and u. So we have a, the lattice translation vector, and u. U is an integer. U could be any integer, and if we were standing on 1, this vector r will land us on another point on the lattice. So let's do some quick examples of this. I could draw this vector. Let's call that R1. R1 is 2 times A, the lattice translation vector. The magnitude of R1 is simply 2A. I could draw another vector from this lattice point over here. I could draw it to this one. We'll call this R2. R2 would be 1, 2, 3. R2 would be minus 3 times the lattice translation vector A. The magnitude of R2 is simply 3A. I'd like to stress a very important point now that I think is missed in many introductions to crystallography. This is just a point. It is not an atom. Not an atom. This is a very critical distinction to make. These are simply points, mathematical constructs with no volume or mass. They don't have any protons or electrons or neutrons. Later on, what we're going to do is start defining bases. And through the concept of a basis, we will put atoms onto the lattice points. But right now, we just have points. So I would like you to really ingrain that in your brain. Not an atom, just a point. In the next video, we are going to start stacking these lines to form a two-dimensional lattice or a plane. I hope to see you there.